So number 19 on the copy.
Okay, number 19 on chapter 6?
Yeah.
Okay.
One part of it, the last part.
Okay, can you just read it out?
It wanted the formula for Hg2 2 plus.
All right, for cations, there are two polyatomic cations that you have to memorize. This is one of them, and the other one is H4 plus. And so whenever you see Hg2, 2 plus, like in a compound, you may see like 2 mercuries, but are those 2 mercuries plus 2 or plus 1? In this case, what is the charge on each mercury? Plus 1. And so this one is called mercury 1. And this is just straight memorization. Mercury is a weird one, so it's got this thing where when we look at the mercury here, they're actually bonded together. And so we're going to have 2 mercuries that are actually bonded together. Each one of these is going to be plus. And so this is why we call it plus 1, except they're not separate. Like when you look at most of the other plus 1 cations, they're individual. Like mercury, this one is an individual ion, so it doesn't bond to another one. Actually, mercury 2 should be a little bit smaller. Do you know why? Mercury 2 should be a little bit smaller. That will be 2 plus. It's going to be a little bit smaller because the fewer the electrons you have, the more the nucleus is going to pull in those electrons closer and closer, and so it actually shrinks down. But here we have this is called a monatomic ion. But mercury 1 is not a monatomic ion. This is a diatomic or polyatomic, either way. And this is just straight memorization. This is what's observed. The next question is, why is it? Why is mercury 2 a monatomic, but mercury 1 a diatomic? The more we can understand about that, the easier it is to predict such things. But for right now, the first step is just to memorize without having a deeper understanding of it. It's fine. And so those are 2. The second one's called, this one we just memorized, ammonium. Versus ammonia, what is the formula for ammonia?
NH3.
NH3. Ammonia is not an ion. There's no charge on here. It's just a neutral compound. We say compound. Usually compounds that are formed from nonmetals are molecular. And so nitrogen's a nonmetal, hydrogen's a nonmetal. So if we have a compound that's formed from nonmetals, it's usually molecular. There are exceptions, though. That's not a law. That's a rule. And rules have exceptions to them. So, do it like that.
For this one right here, Hg2, I subscript 2, I couldn't understand how that was mercury 1 iodide.
That's not mercury 1.
That's what I think.
There must be a mistake somewhere. That should be mercury 2. Unless it's Hg2 I2.
Yeah, Hg2 I2.
If it's Hg2 I2, then I is fixed charge. That's monatomic. What's the charge on I? And what do we call I? Yeah, I is iodine, the element, and if it's an ion, what charge does iodine like? -1. It's one of the halogens. So if we have two iodides that are -1, that means each mercury must be +1 to balance out the charge. But mercury doesn't like to be alone. Iodide's fine being alone. You know, this is not iodine. Iodine is neutral. There's no charge on that, and that's what we call the element iodine. It likes to pair up and be diatomic. So this is not iodine. This is two iodides. And the iodides don't have to pair up. You know, for example, aluminum iodide would be 3 iodides. Sodium iodide would be 1 iodide. You know, we just need enough iodides to neutralize a positive charge. And so this is not iodine. It's 2 iodides. And then mercury, mercury doesn't like to be alone. And so these two are going to have to bond together, like we showed over there. And so this would be called mercury 1 iodide. Now, there are 2 charges for mercury, mercury 1, which is the lower one, and mercury 2, which is the higher one. And there's a common naming system, which is becoming more and more scarce. But there's still old chemical bottles named mercuric and mercurous. So this would be mercurous iodide. That would be mercuric ion over there on the right. You don't have to know those.
So can, the way the book has it, just so I can clarify this, it's Hg and the 2 is in front of the I. Is that a mistake?
The 2 is in front of the I. That's a mistake.
Okay.
Like this, is it written as a coefficient?
Yeah, it's written as a coefficient.
Like that?
Yeah.
Yeah, that's wrong. No, it should be a subscript. There's a difference between coefficients usually indicate how many of these we have. So I could have any number of these. So for example, this is 1, but we never write 1 here. I could have 2 of these, 3 of these, 32 of these, you know, as many as I want. You know, but we never change the subscripts. So if I had 2 of these, I'd never say Hg4I4, you know, to indicate that I have 2 mercury 1 iodides. You know, we only change the coefficient in the front. It's like water. You know, if you have 2 water molecules, you don't call it H4O2. Sometimes water molecules can cluster, and form species that consist of water molecules that are linked together. That can happen. Okay. What were the other questions?
I was wondering if there's a difference between ethylene and hydrocarbonic acid.
Ethylene and hydrocarbonic acid? Hydrocarbonic acid, you know, there are multiple ways you can name certain things. Multiple ways. If we have hydroic acid, it tells us what is the anion end in. It's ide. Good. And so if the iodine ends in ide, then we would say this would be carbide, because there's no carbonide. And so if it's carbide, then what's the charge on carbon as an anion, negative charge? What does carbon like to be if it's an anion with a negative charge?
-4.
-4. We can see that from the periodic table here. Carbon's kind of in this central position where it could either gain or lose 4. If it gains 4, it'd be like neon. If it loses 4, it'd be like helium. That's 6. Well, it's an ide. If it's an ide, it's got to be negative. If it's negative, it must have gained 4. And so this would be C4 minus. It's an acid, so the cation on the acids are all the same. Whenever we have an acid, the cation is H+. The cation is the positive ion, the anion is the negative. And so carbide would be the anion. And then when we make an ionic compound, like an acid, we need to have enough H pluses to balance out the negative charge here. And so how many H pluses will we need to balance it out? 4. And so this is H4C. But sometimes we can flip the order, like 4CH4. So we know this one. There are a couple of reasons. We know this one because of the common name. What's the common name for this?
Ethylene.
This is not ethylene.
Methane.
Methane. This would be methane. Ethylene would have 2 carbons. And ethylene is going to be this, CH2CH2. And the structure is quite a bit different. Well, did this go through organic? Chapter 6 did. Chapter 6, I don't recall. I don't think we went through organic in chapter. Did they go through organic in chapter 6?
Like the structure.
No, math. Are you familiar with organic? Oftentimes what we do is we name the compounds depending on how many carbon atoms are in the chain. And so meth refers to 1 carbon, F refers to 2 carbons, pro 3, but 4. Did the book go through that? Then yeah, you don't have to worry about it. And so the difference between ethylene and methane is 2 carbons versus 1 carbon. And then ethylene has this weird thing. It's going to have a double bond, what we call, but we haven't talked about bonds yet. So we'll talk about that later. But both of these are hydrocarbons. And hydrocarbons are all electron-rich species. Hydrocarbons act as fuels and something that we can oxidize to produce energy. There are some bacteria that eat methane, as fuel. Methane's a pretty good fuel. Why? What makes a good fuel? Like something that burns makes a good fuel. Methane burns. It's a good fuel because fuels are all
Electron core.
electron rich, like metals. Metals are electron rich, they can burn. If you have a metal fire, they're pretty dangerous. I used to think metals couldn't burn, but that was wrong. Until, so when I thought, why are we taking steel wool? I told you, did I tell you that? In the Boy Scouts, I was thinking, why are we taking steel wool? Steel wool's not going to burn. Why are we using it as a fire starter? That's what I was thinking. But then it could burn quite nicely, actually. It burns really well. Anyway, so electron-rich species are this. So there's some bacteria that take advantage of this fuel, methane, and they can digest. Also, things like hydrogen sulfide. There are bacteria that eat this stuff too, or microbes, that eat this stuff. Is this electron rich? Well, what are the oxidation states? Did you guys go through the oxidation state rule? That's good. And so what goes first, hydrogen or sulfur? Usually hydrogen goes first, and hydrogen is going to get its charge of +1. We go group 1 and then hydrogen. So if this were sodium, we'd do sodium before hydrogen. So hydrogen goes first at +1, and that means sulfur is?
-2.
Yeah, -2. And so these are the there are hydrogen sulfide eating microbes, like deep sea and volcanic vents and that kind of stuff. They find them, and so this is fuel for them. This is food fuel. This is food. We wouldn't be able to eat this. So. And you probably don't want to eat this, although maybe we could digest this. Hydrogen sulfide. And you might have eaten this, rotten egg, if you've ever had a rotten egg. But this is different than water. If you think about water, water is the same, but there's a big difference. Oxygen was -2 versus sulfur was -2, Oxygen's small, it's got that -2, it's good. Sulfur's big, a lot bigger. And so sulfur can lose those electrons much easier than oxygen. Are there microbes that eat water as fuel? Not that I'm aware of. Have you ever heard of a microbe eating water for fuel? No, but there are microbes that eat hydrogen sulfide as fuel, and that's the difference because a -2 on oxygen versus, even though they're in the same family, versus -2 on sulfur are quite a bit different. This is what we call electron rich. This is not electron rich. This is happy as is on water. I just saw something about H2S. I forgot exactly what it was over the weekend. I saw something about H2S. In the news. News of microbes. There's bacteria that produce it, but there's also bacteria that eat it. No, found exactly what it was. H2S forms an important source of metabolic energy, fuel, for the microorganisms inhabiting such niches, reminiscent of primordial Earth. That's what I saw. Okay. Does that answer the question for that?
Yeah.
What other questions?
I was just wondering how we know when to use prefixes. I know that it has to do with the difference between it being a molecule and an ionic compound, but I don't know how to tell the difference just looking at the formula.
Okay. If the easiest way, this is unfortunately this is not a law. This is just a rule, so there are exceptions to the rule. But if you have a molecular compound versus ionic. This would be an example of ionic compounds because mercury is a metal, iodine is a non-metal. So whenever we have a metal and a non-metal, we're going to assume that's ionic. We don't have to use the prefixes because the charge on the ion is going to tell us. And the charge, how do we figure out the charge? Well, they're either going to tell us mercury 1 or we're going to see it here. We can figure out what the charge is. Something like this. This is non-metal, this is non-metal. So compounds of non-metals are going to typically be molecular. You only know how to name one type. And the one type is binary. That is 2 elements. If there are 3 elements, like a CHO, then forget it. You're not going to name it. And so if this is binary, then we can name it. We could name this, but the problem is carbon. Carbon's charge varies from what to what? Carbon's charge varies from -4 to +4. And so we don't know what the charge is here. And so what we would call this, I told you there are many ways of naming this. Nobody ever calls this hydrocarbonic acid. I don't know why they used hydrocarbonic acid in the book because that is so rare. Methane is one of the worst acids you can have. You need a super base to get it to react. It's not a very good acid at all. So if it's on that chart, it would be at the very bottom of the chart in acid strength. The other name for this, we could call it carbon tetra hydride. Or we could call it tetrahydrogen.
Monocarbon.
Yeah, we can call it, but usually we leave the mono on or off, depends. So sometimes we'll put mono, sometimes we'll leave it off. So if you call this tetrahydrogen monocarbide, that's okay. Or you can call this tetrahydrogen carbide. And so that makes a difference because the I gets a negative charge. So if we call this carbon tetrahydride, that's telling me that the hydrogens get the negative charge. And if we call it tetrahydrogen carbide, that's telling me the carbon gets a negative charge. And so more accurately, this would be called tetrahydrogen carbide rather than carbon tetrahydride. But all these names are names for the same thing, which is methane. And so let's take a look. So we can see these names, the variations of the names if we go like Wikipedia, for example. Usually what they'll do is they'll give you the various names for this. Let's see if Wikipedia does. So here's some other names for it. Carbane. Carbane, like methane. And carbane is confusing because the carbon, you don't know how many carbons there are. Meth, you do know how many carbons there are. And so methane, when we have the A and A, it's usually hydrogens that are attached to it. In fact, I saw something recently. You could call this aluminum trihydride. That's typically what people call this, or trihydrogen aluminide. The aluminum trihydride is fine for this because metals tend to go positive, and so this works. And hydrogen can go either positive or negative. So aluminum trihydride. But I saw an unusual name for this the other day. They called this alane. It's like methane, with CH4, alane with ALH3. And I thought, oh, that's interesting, alane. This is, they're talking about astrochemistry, cosmochemistry. I don't know, it was with one L or two L's. It was with one L. I'll have to show you the article. But we have others, the others would be like silane. What do you think silane is? If that's methane, guess what silane is?
SiH3.
Close. SiH. Silicon and carbon are in the same family.
H4.
H4, SiH4. This is silane. I used to use this stuff all the time. Silane. I had a big bottle of it. It's very dangerous chemical. The alane was ALH3, and they were talking about water. Find that. So this is a metal and a non-metal. So we would name this as an ionic compound. So naming this as an ionic compound, we would just call this aluminum hydride. But when you look at the Wikipedia, you can see there are other names too. So carbane's not really recommended. Marsh gas, natural gas, carbon tetrahydride, and hydrogen carbide. There's one more name for this that's often seen. Because carbon hydride doesn't really tell us what hydride it is. So people will go carbon, Roman numeral 4, hydride. And so this is a compositive name. And so what we can do is we can name these so many different ways that we probably should just stick to one way. And sticking to one way is, if it's a binary molecular, we're going to name the first element as is carbon, and then the second we'll use the prefix tetra and then hydride. So this would be carbon tetrahydride. It's not really accurate. This would be more accurate, tetrahydrogen carbide for this. But it's all right. And then if it's ionic, we'll just name the cation aluminum and the anion hydride. We aren't going to use prefixes because we'll figure it out. Aluminum's 3+, hydride's 1-. So we'll know we have 3 hydrides for every aluminum. This is not a binary molecular compound. We would never call this nitrogen tetrahydride because this is an ion, it has a charge. And so it's only for neutral compounds like this that we would use that. And so there are just two things. Is it an ionic compound, metal and nonmetal, or molecular compound, all nonmetals? And then we'll name it. What happens if we have a semi-metal? A semi-metal is like in the border region between metals and nonmetals. Like here, these are called metalloids. Like for example, it says metalloid here, metalloid, metalloid, metalloid. Aluminum they call a post-transition metal. So they call aluminum a metal, boron's a metalloid. Carbon they have ranked as a non-metal. And so it's this color here that's the metalloid. With those types of things, we can go either way. You know, we could either name it using the prefixes, or we can name it as an ionic. So either naming system is okay for that. Okay, other questions?
So if we use like the Roman numerals, but it doesn't have variable charges, like if I were to name alane aluminum 3 hydride.
That would be wrong.
Okay.
That would be wrong because aluminum only has one charge. And since it only has one charge, we would name it aluminum hydride. That would be it. So you can pretty much tell what's going to have one charge. These first 3 columns, these first 3 columns in this aluminum gallium. Everything else is variable charge except for 3 in this variable charge region with 3. Yeah, silver, zinc, and cadmium. Those 3. Zinc, I saw some news about zinc recently. Do you know where they find zinc atoms? Not ions, zinc atoms. Or maybe they are ions. I don't know if it's ions or atoms. It turns out that antiques have zinc atoms or ions. It'll be, I should find out. It's got to be ions, I would think. Zinc ions on the edges, making them particularly. They say antiques can bite through extremely tough materials, and the amount of force they use is like 60% less than human teeth do the same thing. Antiques and zinc. And so they did an atomic scale imaging to determine that there's zinc atom coating turns antiques into tough, sharp tools. It was done at the University of Oregon. Yeah. cures materials using only 60% or less force than would be required for human teeth. So remember, zinc, cadmium, and silver, those are fixed charge. That's a little island of fixed charge. Never use a Roman numeral for those, but use a Roman numeral for everything else. Okay, other questions?
Aluminum. I just want to, you want to write this down?
Okay.
So it's Al, open parentheses, HTeO4, close parentheses, and 3.
This one's a tough one. I'd say the nomenclature in this book is tougher than the Chem 1A book, probably. But the first thing is this, this is the cation. This one, which should be easy. What's the charge on aluminum? 3. And that means this whole thing is the anion, and that must carry what charge? TeO4, HTeO4 must carry a net charge of -1. And we have 3 of those, and so it's all balanced out. But whenever we have H, we call H, if it's at the front, when H is at the front, we call it an acid. This is why when I did hydrocarbonic acid, it came out in the front, the hydrogens, like this. But typically we write it like this, because these aren't very acidic hydrogens. But whenever we have H, we typically think of acid. This is an acid, and then there's a charge on here. It's a negative charge, so we call it an anion. So this is an acid anion. And so acid anions are actually pretty easy to name, because what we do is we take the acid, H+, and we call that hydrogen, and then we take the anion. So if we remove the H+, what are we left with? We're left with TeO4. What would the charge on it be?
-2.
Yeah. So TeO4, we'll call it 2- here. And so this is what we need to figure out. So the thing is, when there's an oxygen, it's got to end in a T. So is this 8? Is this ite? Is it per 8 or hypoite? We have to figure this out. So it's tellurium. When there's oxygen, it's got a T. If it's got a T, then we have these 4 choices. This is tellurate, tellurite, pertellurate, or hypotellurite. And so we have to figure that out. And looking at the periodic table, we should be able to figure it out. Look at the periodic table, and it is going to be tellurate. Right. How did you figure that out?
Because it's under sulfur, and sulfur would be SO4 2-, so it follows the same pattern.
Yeah, good. That's how you figure it out. We would know, I would start off with this one. Silicon forms silicate. And how many oxygens does silicate have? 4. And what's the charge? So this is SiO4 4-. Phosphate would have how many oxygens? 4. And the charge? So SiO4 4-, PO4 3-. Sulfur would form SO4 2-, and then we go down. Selenate would be SeO4 2-, tellurate would be TeO4 2-. So that's perfect. And so this is tellurate. And so we name this hydrogen tellurate. And so that will be aluminum, hydrogen tellurate. Sometimes we use the bi, BI, or bitellurate. aluminum bitellurate. Bi is a very common name, so that's why you should know that. Any other questions?
So the pattern we were talking about is silicate, phosphate, and
Yeah, the pattern you should know. I don't know what your preference is. It's a handy pattern to know. Can you I only have these small ones.
because I struggle figuring out which one's like a 3, which one's a 4.
It's just memorization. The pattern is this. You see this row and this column? How many oxygens are in this row and this column? This one we start with borate. How many oxygens and charge on borate? BO3 3 minus. Carbonate? You got to do this. This is like your mantra or whatever. You got to chant this. What is this? Borate is BO3. Carbonate.
CO3 2 minus.
Nitrate.
NO3 minus.
Fluorate.
FO3 minus.
Chlorate.
ClO3 minus.
Bromate.
BrO3 minus.
Iodate.
IO3 minus.
Do you see that? Just keep repeating that over and over again until you get it. Then you'll have no problem with these here. And so just one more time. Borate.
CO3 3 minus.
Carbonate.
CO3 2 minus.
Nitrate.
NO3 minus.
Fluorate.
FO3 minus.
Chlorate.
ClO3 minus.
Bromate.
BrO3 minus.
Iodate.
IO3 minus.
See, how many times do we have to do that until it's memorized? I don't know, hundreds maybe?
Yeah.
All right. Okay, silicate.
SiO4 4 minus.
Yeah. Phosphate.
PO4 3 minus.
Sulfate.
SO4 2 minus.
Selenate.
SeO4 2 minus.
Tellurate.
TeO4 2 minus.
Arsenate.
ASO4 3 minus.
Good. Antimony. Antimony.
Antimony.
This is antimony, so antimony. Something like that.
SbO4 3 minus.
Yeah. Germinate.
GeO4 4 minus.
Yeah, you got it. You guys have it memorized. So the rest of you just keep doing that over and over again and you'll be all right. Don't you think? Maybe it's not too bad, right? Maybe? Or is it too bad?
It's very bad.
It's very bad? Very, very bad?
Write it down. Yes, and that's easy.
Okay. Just write it. Keep either can it or write it down or do something. But the thing is to start, trying to memorize those. Okay. And so there are only 2 choices of oxygen, 3 or 4 for the 8. That's all. But then you have the variations of that. Because if you memorize the 8s, you don't have to memorize the ites. Did I have you memorize the ites? I don't have you memorize the ites because if you memorize the 8s, the ites are easy. It's just 1 less oxygen, same charge. And the hypoites, okay, 2 less oxygens than the 8s or 1 less oxygen than the 8. Hypo means lower, per or hyper means higher. And so the per 8s are going to have 1 more oxygen than the 8s. But not everything forms hypo, not everything forms per, and not everything forms ites either. And so these are the choices, but if you memorize the eights, then you're okay. But there are some eights that aren't on that chart that are more difficult to remember sometimes. Like the ones I talked about, oxalate. Oxalate's a pain to remember. And so, you have to have some kind of thing to remember it. I probably did this. I probably did 2, 4, 2. 2, 4, 2. 2, 4, 2. 2. 2, 4, 2, 2. And so I probably memorized it using a number pattern. I can't remember. But acetate I definitely memorized using a number pattern. 2, 3, 2. 2, 3, 2, 1. So we have, then if I remember the number pattern, 2, 4, 2, 2, all evens. Even, odd, something like that I'll do to help me memorize it. And so acetate is a pain, oxalate's a pain. This is wrong, sorry. See, I even didn't get it right. 2, what is it? C2O4, 242, that's it. 242. I don't know why I threw in the H. And so, yeah, 232 minus. What else? Permanganate. This one is difficult to remember. MnO7 charge. People always screw up the charge. So, for example, some people will put a 2 minus charge on there, permanganate. But that's wrong. So there are different tricks to memorizing this. One trick is manganese is maxed out. If manganese is maxed out, what is its positive charge? The max positive charge, the periodic table shows us the max positive charge, would be 7. Over here, if I have 7 oxides,
Permanganate, isn't that O4, not O7?
yeah, right. So this is getting back to, if manganese is maxed out at plus, what was it? Plus 7, then does this work? No, it can't be there. This can't be it. And so what we do is there are certain tricks you could do to try to remember it. Although this one's a bit tougher. It's not MnO7, it's MnO4. And if it's MnO4, then what is its charge? So if we have 4 oxides, 1, 2, 3, 4, then the total negative charge is -8. Total positive charge is +7. That means this charge is also wrong, and the charge should be -1. And so there's certain things you could do, to check it. If you know that permanganate's maxed out, and then you can see what the number of oxygens and the net charge makes sense. So does this one make sense? So if manganese is 7, and then we have 4 oxides, let's say, or 4 oxygens with 2 minus, then it works out because we have +7 plus a -8 is going to give us a -1. And so this works out. So it might be hard to remember, MnO4 minus, but there's a way you can check it. And so if you screw up the number of oxygens or if you screw up the charge, then it's not going to work out where manganese is +7 and oxygen is -2. The numbers aren't going to add up. And so that, in case you forget, might be a last-ditch effort to try to get the correct one there. So we have permanganate, and then we have
Dichromate.
dichromate. Dichromate, we might try to do this, Cr2O8, because chromate is CrO4. But this one doesn't work out either. Dichromate and chromate have the same charge at 2 minus. Chromate's maxed out, and so this makes sense. Chromium doesn't max out at 7 though. Chromium maxes out at 6. So if this is chromium 6, and we have 4 oxygens at 2 minus, so that's plus 6 minus 8 is going to give us minus 2. And so this works out. And this is also chromium 6. So if I do Cr2O8, it doesn't work out. Because if the chromium is supposed to be 6, because both of these are chromium 6, and then I have the 4 oxygens at minus 2, it doesn't work. Because plus 6 is going to give them plus 12. Plus 12 minus 2, 4, 6, 8. Oh, I got 8 of them. So 16. 1, 2, 3, 4, 5, 6, 16. So plus 12 minus 16 is minus 4. Well, that's not, and minus 4 is an unusual charge. And so it turns out that this is Cr2. We have to lose one of the oxygens. So it's Cr2O7 to get them to link together. Oxygens don't like to link together. And so chromium has 4 oxygens attached to it like this. And if the oxygens link together to form a dichromate like this, we form what's called a peroxide bond. What do you know about peroxides? This is called a peroxide bond. Are peroxides stable or unstable?
Unstable.
Unstable. Peroxides are unstable. Think hydrogen peroxide. And so this is why we have to lose one of those oxygens. One of these oxygens has to be lost so we do not form a peroxide bond so we can have a stable dichromate. And so technically it's not 2 chromates. It's 2 chromates minus an oxygen. So we don't get a peroxide bond here. Speaking of peroxides, I saw an interesting article.
So how do you know dichromate is Cr2O7, 2 minus? What's the concept behind that?
How do I know?
Yeah.
Well, if you know the chromate, is CrO4 2 minus, then dichromate should be 2 chromates linked together.
Okay.
That's, di usually refers to 2, like mono, di, tri. So dichromate, we expect 2 chromates to be linked together, but we end up losing one of the oxygens. So it's rather than Cr2O8, which would be 2 chromates, it's Cr2. And the other thing is the charge. The charge is weird because the charge is the same. Shouldn't it be double the chromate's charge? Shouldn't it be 4 minus? But it isn't because of the structure of things. You know, one of the observations about respiratory viruses, the seasonal variation in respiratory viruses, like summer is kind of low transmission of respiratory viruses. Winter is much higher transmission of respiratory viruses, right? So that's an observation, that's a pattern. Is that a consistent pattern, would you say? Pretty consistent pattern? Could you call that the law, the law of respiratory viruses? Yeah, maybe, maybe not. Depends on how good of a pattern it is, right? But maybe a pseudo law or something like that. A rule. A rule would be much weaker. But there's a pattern there. Do you have a hypothesis for that? Why is that? There are different hypotheses for that, right? Let's see. Well, I saw a very interesting hypothesis for this. I got that backward. Why this makes me sign in so many times. Do you guys have this issue with the El Camino email? Why doesn't it do that? I guess I didn't. I thought I emailed it to me last night. I guess I forgot to do that. All right. Well, basically, but this is a professor at Stanford. What he's saying is that his hypothesis of why the flu virus and other viruses are seasonal is because of the humidity. And he says that these water droplets in air can actually form hydrogen peroxide. And he said there's some interesting surface chemistry where there is some formation of hydrogen peroxide in these microdroplets. They've done studies where there's some ozone in air. A little bit of ozone in air will create hydrogen peroxide in the water vapor. And so between 40 and 60% relative humidity is the optimum humidity to prevent respiratory viruses because that's the optimum concentration of hydrogen peroxide. Less than 40% humidity, the droplets evaporate too quickly, and greater than 60% humidity, it's too dilute, the hydrogen peroxide. So he's saying that it's hydrogen peroxide that occurs naturally in these droplets that kills the viruses. It's pretty interesting. I'll show you the article later. And so, if you have a dehumidifier, you don't want to go too low in the humidity. To keep the humidity up. Basically. Okay, were there any other questions on this chapter? Okay, we finished talking about chapter 7. I didn't do too many of the problems there in chapter 7.
Did we talk about hydrates
Briefly.
briefly?
Hydrates, you just add, how many waters. You could use a prefix for those, dihydrate, trihydrate, or you could just number them, 2-hydrate. And so you just add that word at the end. Hydrates are actually solid. I think did I show you copper 2 sulfate?
Yeah.
You can tell that both of them are the same. This is copper 2 sulfate, this is copper 2 sulfate. But what happens is copper 2 sulfate can pick up moisture from the air. You don't need to add water to this. If the air is humid, then what happens is it becomes like this. So we call this desiccated. If you're out in the desert, this is what copper 2 sulfate would look like out in the desert, all desiccated, totally dried up. Near the coast, it's going to look like this. Or if you're near a large body of water where there's humidity, that humidity gets picked up. This is still solid. This is not wet. It just absorbs some water. And so we call this the hydrated form. It forms a pentahydrate. Penta means how many waters? 5. So copper 2 sulfate pentahydrate would be copper 2 is 2 plus, sulfate is SO4 2 minus, and pentahydrate is 5 H2Os. Here. Now, normally we write a subscript, but for hydrates we don't. And so we just do this. We do CuSO4 dot 5 H2O. This number can vary. This is what we call saturated. This would be the max. If we start heating this up, it starts to dry it out. And as we start heating it up, we'll go to 4 waters for every copper 2 sulfate formula unit. 3 waters, 2 waters, 1 water, no waters. Once we hit no water, then it's just SO4. This is called anhydrous. Anhydrous means no water. Anhydrous. You can see it here. Anhydrous. And so on the right, we have the pentahydrate. On the left, we have the anhydrous. Copper 2 sulfate. Here it is too, anhydrous. This is beautiful crystals of copper 2 sulfate pentahydrate here. Very nice crystals that it forms. And so it's totally solid. Those waters just get incorporated into the crystals. We can dry them out. You take this nice crystal and start heating it up, and it turns into this kind of powder, dry powder. Here they're showing it. Anhydrous picking up 1 water, 3 waters, 5 waters. Where do the waters go? Waters are stuck in there, in the crystal structure, we call it. So this would be the crystal structure, the lattice, ionic lattice, and water would be stuck in here. You don't have to worry about that. So these are typical questions from chapter 7, like this. 1, how many sodium ions and how many chloride ions are in 0.01 grams in a 0.01 gram grain of table salt? How is this ion ratio expressed in the formula in general? This small group discussion. Skip that. Well, those are some calculations. So we talked about molecular mass and formula mass. So like this, lithium chloride, ionic or molecular? Lithium chloride, ionic. So you would, aluminum carbonate, ionic or molecular? Aluminum carbonate, ionic. Ammonium sulfate. Now ammonium sulfate is all non-metals. So ammonium sulfate has this formula, NH42SO4. It's made up of all non-metals, but this is an exception to the rule. This is an ionic compound because it consists of the ammonium ion and the sulfate ion, two ions that we're familiar with. Butane is molecular or ionic? Molecular. That would be C4H10. They even emphasize it over here. So butane, we can name these things binary. Binary means two elements, carbon and hydrogen. So this would be tetracarbon decahydride. Tetracarbon decahydride. That would be our name for butane. Silver nitrate, ionic. Manganese 4 oxide, ionic. Zinc phosphate, ionic. So molecular compounds, if they're binary, we're going to use this. So nitrogen trifluoride, this is binary molecular compound. It consists of nitrogen, a nonmetal, fluorine, nonmetal. And so we're going to use that. And it's binary, there are only two elements. Barium chloride, ionic, lead 2 phosphate, ionic. This one here is sulfur trioxide, molecular compound. Antimony, SBF5. This is the strongest known acid. This is much stronger than that. The strongest acid on our charts is perchloric acid. This is much stronger. This is a superacid, HSBF6. So it's a very special acid. And it's thought of as the strongest acid around. We don't have to memorize this one because it's rare. We don't really use it. Superacids and superbases we don't really worry about because they're too reactive for us. But lots of people use these for chemistry. We have nitrogen dioxide, fog, dichlorine monoxide, mole concept. So calculating masses, we can figure out the masses, mole to number calculations, molar mass, conversions. There's some more dimensional analysis type problems here. So we could take a look at some more challenging problems here. Look at some typical calculations we do. The quantitative significance of take a deep breath varies, of course, with the individual. When one person did so, he found that he inhaled 2.95 times 10 to the 22nd molecules of the mixture of mostly nitrogen and oxygen, which we call air. And so 2.95 times 10 to the 22nd molecules of air. We can say nitrogen and oxygen mainly. Assuming this mixture has an average molar mass of 29 grams per mole. And so it's a mixture. So if I have a mole of nitrogen and oxygen, it's going to weigh around 29 grams per mole. And so we're going to assume air has a mass of about 29 grams per mole. There. What is the apparent lung capacity in grams of air? So how many grams of air did this person just inhale? And so this boils down to the stoichiometry map. The stoichiometry math is something like this so far. We have mass of A. We can convert mass of A to moles of A if we know the molar mass, which we do. So if we have grams of air, we can use this as a conversion factor. This is called the molar mass here. And we can use this as a conversion factor to go from grams to moles or moles to grams, depending on how we set that up. And then from moles of A, we can go to the number of molecules or particles of A using Avogadro's number. And so here in this conversion, we'll use a molar mass. In the second conversion, we're going to use nth of A. Nth of A is the abbreviation for Avogadro's number. We can do that. Or we can go backwards here, it doesn't matter. And so typically you go from grams of A to moles of A to number. But in this case, we're going to go from number of molecules to number of moles, from number of moles to mass. And so we're going to use Avogadro's number here. Avogadro's number says that 1 mole of anything contains how many? And so 1 mole of air is going to contain how many molecules of air?
6.022 times 10 to the 23rd.
Good. 6.022 times 10 to the 23rd molecules of air. Air is a mixture, but sometimes we treat mixtures like this. And so that gives us moles of air. And then we'll use this as the next conversion here. 29 grams of air for every mole of air. And so how many grams of air did this person just inhale? And so let's see what that comes out to. So I'm going to go 2.95 times 10 to the 22nd divided by 6.022 times 10 to the 23rd times 29. .42, like we're allowed 2 sig figs because of the 29. This is just the average. You know, the composition of air is not fixed. The composition of air varies. Therefore, the mass of a mole of air varies depending on its compositional makeup here. And so this is just good to 2 sig figs. And so we'll just do 1.42 grams or 1.4 grams of air in that breath. So this is a typical dimensional analysis problem in this chapter. A lot of the problems just do one step. So molecules to moles, or moles to molecules, or moles to grams, grams to moles. And so most of the homework problems are just one step. But here, this is a challenge problem because we have 2 steps in this. Yeah. And we can go either way, left or right. Assuming gasoline to be pure octane, CH18. Gasoline is not pure octane. Gasoline is a mixture of many hydrocarbons. We call these hydrocarbons. Hydro for hydrogen, carbon for carbon, hydrocarbon. Hydrocarbons are great fuels, electron rich. An automobile getting 25.0 miles per gallon would consume 5.62 times 10 to the 23rd molecules per mile. Calculate the mass of this amount of fuel. So 5.62 molecules per mile, 25 miles. So what should I start with in this particular problem? Let's start with 25 miles. Should I start with 5.62 times 10 to the 23rd molecules per mile? Or should I start with the mass of? Well, yeah, I want to know the mass. How is the mass of this amount of fuel? What's the amount of fuel? A gallon? No. So this is a bit confusing because actually we don't need this here. We just need 5.62 times 10 to the 23rd. That's how many molecules per mile. So we can start with this. This is a ratio. 5.62 times 10 to the 23rd molecules of what? Now we're making an assumption. This is going to be molecules of
gasoline.
yeah, but we're going to make an assumption that it's pure octane because gasoline varies considerably depending on who manufactures it. C10, 18 per mile. And so if we're at molecules, then where can we go? Moles. So we know that 1 mole of octane, C8H18, contains an Avogadro's number's worth of molecules. Avogadro's number is 6.022 times 10 to the 23rd molecules. You need to memorize this. And so the molecules of octane cancel. That leaves us with moles of octane. And from moles of octane, I can go to grams of octane if I know the molar mass. So I need to calculate the molar mass. And so I have 8 carbons. What's the average mass of a carbon? 12.01 grams per mole. So 8 times 12 is what? 96.08. 96.18? 08. 96.08. Thanks. Grams per mole. And then I have 18 hydrogens. So it's 18 times, what's the molar mass for hydrogen?
1.008.
Should I use 1.008 or should I use the other one? What was the other one? 1.01. And in this case, I'm going to use 1.01. I'm going to have some round off error, but it's going to make the calculation easier to do in your head. So it's going to be 18.18. All right? It's going to give me the same, the correct numbers. Well, is it going to give me the correct numbers suitcase? Maybe not.
That would only be 3.
Yeah, it's not going to give me the correct numbers suitcase because it's such a large number. Maybe I should do 1.08 to keep it consistent. So let me back to that. We'll do 1.008. And so what is that? 18 times 1.008. I don't want to think. 144. And then add these up. 9608 plus 18.14. 114.22. Okay, we're allowed 2 decimal places. That's what we want. And so over here, I'll have 114.22 grams of octane per mole of octane. And so if I have an Avogadro's numbers worth of these molecules, it's going to weigh that much, 114 grams. And so that will give me the grams of fuel I'm going to be consuming. So 114.22, we'll start from the beginning. 5.62 times 10 to the 23rd. Divided by 6.022 times 10 to the 23rd times 114.22. 106.59 grams. So I'm allowed 366 per mile. So about 107 grams per mile of fuel. What it's going to cost you. So you can figure out the cost from that. But usually we don't buy it based on mass, right? We usually buy fuel based on, gallons, volume. Speaking of fuel calculations, was looking, you know what Tesla uses for their, projected savings? Tesla, I just looked, let me see, hopefully I'm remembering this right, but they use 13 cents per kilowatt hour. And then, okay, so just charged it. Let's say charge the Tesla from, let's say, 36% to 80% charge. And Tesla, he said it costs $3, to charge it, which is $3 pretty cheap. But then I looked at the electricity bill and I looked at the rate. So Tesla is basing the savings on 13 cents per kilowatt hour. But the rate that we're paying is, I think, over 40 cents per kilowatt hour. And so it wasn't as cheap as I was thinking. This is nice because you can see the savings. The savings aren't as rosy. So it's something you can look at.
Better than gas, right?
I don't know. I was looking, if let's say if you have a hybrid, then it's about the same. Yeah. If you have a hybrid, about the same. If you get, let's say you get 40 or 50 miles a gallon, yeah, then you have a hybrid, yeah. So hybrid is pretty good. Yeah. So that would be, and then you think, well, you think about, if you go all electric, then you don't have as much carbon emission, but most electricity produced in the U.S. is from coal combustion, and coal produces a lot of CO2. And then they're converting, that heat into electricity is not 100% efficient. You lose some energy based on that. And the hybrid engines are quite efficient. So I don't know. Eventually, they're talking about making electricity using fusion power. And I watched this very interesting thing on fusion. You know what they're using for fusion? They're using deuterium. Usually when people are talking about fusion, like the sun fusion, this is not exactly like the sun. They're using deuterium plus helium-3. And to do this, deuterium and helium-3 make helium-4 plus a neutron, I think it was. Yeah, neutron. Neutrons are kind of nasty.
This is what a couple of years ago, remember the U.S. and China were both looking to the moon because the moon has huge deposits of helium-3.
Oh, yeah. Yeah, they're looking, this is helium-3. They're talking about how to get helium-3. They're talking about the moon. They're talking about some other sources too for helium. Yeah, this is promising for fusion because helium-4 is really stable. Lots of people want that electron, number 2 electrons. Neutrons, though, are not that great. You know neutrons? Have you ever heard of the neutron bomb? Mm-hmm. Neutron bomb was this idea that they were going to drop this bomb and it's going to shoot out all these neutrons. And these neutrons, being neutral, can collide with the nucleus easily. Like when, you remember, who was that guy who was shooting the alpha particles at the gold atoms? Who's that guy? Rutherford. Rutherford was shooting gold atoms, but the alpha particles, and alpha particles are actually just helium nuclei. Alpha particles were not reacting with the gold nucleus, As the alpha particles got close to the gold, what happened to the nucleus? They got deflected. Right? And so if the alpha particle tried to crash into the gold nucleus, maybe it could fuse. But they weren't going fast enough. In order for fusion, you have to have high-speed alpha particles, and then maybe it'll crash into the nucleus, and maybe it'll fuse to make a bigger one. But these alpha particles bounced off, right? And why did they bounce off, or why were they deflected? The alpha particles were deflected by the nucleus because because of the charges. Alpha particles are +2. Nucleus is plus whatever. You know, how many protons in a gold nucleus? 79, plus 79 in that nucleus. And so they're huge electrical repulsions. And so the alpha particles would not react with the gold nucleus. They're deflected. But think about a neutron. If you have a neutron, is the neutron going to be deflected or bounced off? No, the neutron's going to go straight into the nucleus. And what's going to happen is, if the neutron gets absorbed by the nucleus, then maybe there are going to be too many neutrons. If there are too many neutrons, it upsets the balance, the stability of the nucleus. And so when we have too many neutrons, the atoms become radioactive. And so that was a great idea, I guess, for killing living things, but it makes all the buildings, they were saying the advantage of the neutron bomb is the infrastructure is still there. It doesn't destroy the infrastructure, but the infrastructure is going to be radioactive, you know, for some time. And so because of all the neutrons, so that wasn't anyway, this was, if you can produce electricity like this, and they were talking about the cost of electricity, you know, it should bring down the cost.
So what would be the cost of hydrogen cars? Would that be more expensive than electricity?
Well, it depends on how you generate the hydrogen. There are two types. You know, hydrogen fuel cell is very promising, and there are different ways you can generate hydrogen. They're trying to generate cheaper. Have you heard of what they call violet? There's like blue hydrogen. What is it? Blue hydrogen and green hydrogen. Have you heard of those? Well, we're talking about violet hydrogen right now. It depends on how you make it. Was it turquoise? Maybe it was turquoise hydrogen. Turquoise hydrogen, yeah, that's what it was. They gave all these colored names. It's not because of the hydrogen's color. They aren't colored. They gave the name to how it's being produced, what kind of reaction they're using to make it. Usually when they make hydrogen, there's a startup company. There's a professor at UCSB. I took a class from him. This professor at UCSB, I remember him because this guy got his chemical engineering degree. It was in the chemical engineering department. He got his chemical engineering degree at like Berkeley, and then went to MIT, got his PhD in chemical engineering, and then went to Harvard and got his MD. And then I was looking at the timeline. He got his PhD and his MD within a year of each other. I don't know how he did it, but I took a class from him. At the time, what he was studying yeast. And he had this yeast, and he was bombarding the yeast with gamma radiation, and then looking at their metabolism of phosphorus, phosphates. And so I thought, oh, that's pretty interesting, to see what kind of damage comes from radiation. Well, then I just read he made a startup in Santa Barbara and Goleta there, and his startup is to make turquoise hydrogen. Turquoise hydrogen is kind of expensive to make. But he's making turquoise hydrogen. Turquoise hydrogen, normally when you make hydrogen, like you use something called the water gas shift. Water gas shift is you take methane and then you steam. And you react methane and steam and you make hydrogen gas and the other product. Methane and steam makes hydrogen gas, and what do you think the other product is? You probably can guess the other product. What do you think the other product is? CO2. This is one of the cheaper ways of making hydrogen, but it's energy intensive. But it may not be the cheapest way of making hydrogen because it's making CO2, and CO2 you have to pay a tax for. It's a carbon tax now. And so, what his startup is, what was it called? C0, carbon zero. So they have a website too. Carbon zero. This is it. So the problem is normally when you make hydrogen, you create a lot of CO2, and now with the carbon tax, it's not going to be economically feasible. And so his thing is he doesn't use steam; he uses these proprietary molten liquid. And this proprietary molten liquid, he bubbles the methane through, and it creates hydrogen, but it gives off not CO2. Do you know what it gives off? Carbon, as like soot. So what he does is he takes a natural gas, generates the hydrogen, and gets solid carbon, like coal, basically. And so the interesting thing is this: he says that what do you do with all this coal? One of the things is, okay, you could burn it, but that's going to create CO2. So the way he makes it C0 is he proposes to take all that coal that he's generated, this soot, and bury it back into the coal mines. You know, the coal mines in West Virginia, Pennsylvania, and all those places, Utah, you know, where they have coal mines. And then there's going to be no carbon tax, basically. And so, although it's a little bit more expensive to generate, if you factor in the taxes, then he said it's going to be economically feasible, and I guess a lot of people agree with that. And so, rather than making CO2, he's trying to make C here. Otherwise, CO2 is it's not so great. So hydrogen is promising, but I have another friend that was working on photovoltaics and splitting water. You know, one of the big things about hydrogen and the hydrogen economy is water is so plentiful. And so if you could use solar energy to what we call electrolyze water, then you can generate hydrogen that way much more cheaply. There's no infrastructure for it. Like, you know, the good thing about like electric right now, you know, there are a bunch of charging stations, but sometimes the charging stations get backed up.
I know there's a company called Nikola that partnered with Budweiser in California to use hydrogen for trucks.
Oh, wow. All right. Well, you know, around here is pretty cool because we have, 2 hydrogen stations. You know, on 190th, there's a hydrogen station there. And then on Prairie, there's a hydrogen station there. So you can fill up with hydrogen. I talked to this guy who bought a hydrogen fuel cell car. Did I tell you this? You know, the thing I'm worried about is hydrogen's a compressed gas. And so what happens if there's a collision, you know? Yeah, and like the Hindenburg wasn't a compressed gas. Hindenburg was just a balloon filled with hydrogen, and the pressure inside the balloon was the same as the pressure outside. So that was at atmospheric pressure, which is mostly empty. space. But in this compressed gas, you have a lot of hydrogen. They probably want liquid hydrogen, or even better. Have you ever heard of cold fusion? Cold fusion? Cold fusion got a lot of ridicule, but I thought, wow, what an idea. I mean, there was some reasoning for this. The reasoning for this is hydrogen. Hydrogen, as far as fuel density goes, is it's the same thing with methane and any gas. If you have a gas, there's a lot of empty space. If you have a lot of empty space, that's dead space that you can't use for fuel. And therefore, the range is very short. So for methane vehicles, I was looking at methane because I was thinking, oh, that would be kind of cool. There are two types of methane vehicles out there. There's one that just burns methane, and there's one that converts the methane and air into electricity. And those are called fuel cell ones. Well, there are a lot of CNG vehicles, including buses, and I thought, well, that's pretty interesting. But I went on the users group and I'm reading some of this stuff, and a lot of these people make these illegal spare tanks because in case they run out of methane, they aren't going anywhere, and there aren't that many methane stations out there, right? And so they have another bottle of methane stored in their trunk or someplace, which is dangerous, if you have compressed methane there. But they do that because they're really afraid of running out of gas. Well, same problem with hydrogen. But people, I wouldn't put a spare hydrogen tank in your trunk. That'd be pretty dangerous. But what people were looking at storing hydrogen at higher densities. And so rather than gaseous hydrogen, they should use liquid hydrogen. And so if you use liquid hydrogen, you'll have less empty space and then greater fuel density. But there are some researchers that were studying hydrogen dissolved in metals like palladium and platinum. And it turned out that the density of the hydrogen in these metals is actually higher than the density in liquid hydrogen. And so you could pack more hydrogen when it's dissolved in a metal than when it's a liquid or even a solid. And so what they're saying is that these hydrogens are packed so tightly, they might actually be forced together close enough that they can fuse the nuclei together. And if they can fuse the nuclei together, then you don't need high kinetic energies and lots of heat. And so this is where cold fusion came in. But I'm not sure on the tanks for the person I knew about this Katie Philstone. And he said that before he bought it, they showed him a video. In this video, they took the hydrogen tank and dropped it out of some jet airplane. I don't know how many thousands of feet of elevation, and it fell down to the desert and didn't explode. So after he saw that, then he said he felt pretty safe because he thought, if there was ever a bad accident, it's probably not going to explode. But anyway, all right, let's take a break now, and we'll start again. All right. What we're going to do is, if you have questions on this Chapter 7 homework, you can ask me about this. We're going to take a look at Chapter 8, though, now. Chapter 8 deals with chemical reactions. So if we look at the topics, evidence of the chemical change, evolution of the chemical equation, balancing chemical equations, interpreting the chemical equations, writing chemical equations, combination, decomposition, single replacement, double replacement, summary of reactions. So, oops, sorry. This one, if we look at this, a space shuttle here, they're getting liquid hydrogen. Hydrogen is normally gas, but they're probably going to use liquid hydrogen and liquid oxygen. That way they can get rid of a lot of the empty space. When you look at the fuel tanks, for something like the space shuttle, it's not wasted. They're packing as much hydrogen and oxygen as they possibly can. And so they're taking liquid hydrogen and liquid oxygen, and when you react those two, oxygen wants two, hydrogen loses, and we form H2O, water. That's an example of what we call an oxidation reduction reaction. Oxygen is an oxidizer, hydrogen is a fuel or the reducer. So we have a lot of reactions that are like that. This is balanced. You see, it's two hydrogens, one oxygen to form two waters. And hydrogen is diatomic, oxygen is diatomic. Okay, we have different names for certain things, like reactants and products. And so the reactants in this are the things on the left. So the two hydrogens and oxygen, those are the reactants. The product is on the right. So these two waters are the products, the reactants and products. This arrow just means yield or produces. The reaction yields water or produces water. That's the arrow. Okay, there are two ways of visualizing something like this. One way of visualizing a reaction like this is in terms of particles. So two hydrogen molecules react with one oxygen molecule to form two water molecules. The other way of visualizing a reaction like this is by moles of molecules. So 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. Or dozen. 2 dozen hydrogen plus 1 dozen oxygen yields 2 dozen waters. And so we can do individual particles, we can do dozens of particles, or we can do moles of particles, and it's all the same ratio. However, this is not mass. So if I had 2 grams of hydrogen, would 2 grams of hydrogen plus 1 gram of oxygen produce 2 grams of water? No. And so balanced equations like this are not based on mass. Balanced equations like this are based on the number of particles or the number of moles of particles that we have. Evidence of chemical change, it's pretty obvious here that there's going to be a change. We're losing the hydrogen, we're losing the oxygen, and we're replacing it with water. So the properties of these are totally different, hydrogen, oxygen, and water. And so what we're looking for are changes in properties that's going to give you indications that a chemical reaction has occurred. So evidence, certain things like this, color change. The color change might not always be a chemical reaction. Formation of a solid product. Formation of a solid product is called precipitation. And so what we might have is, we might have precipitation of a solid. That is, there was no solid there before, and then all of a sudden there's a new solid that comes. Or formation of a gas. Gas formation is called effervescence. So we have precipitation, effervescence, color change. Other indications might be heat or light. You might feel it getting hot or cold. You might see light being produced. So we're looking for evidence of chemical change. Now, like in this case, they're mixing these 2 liquids together. Initially, it starts off as purple like this, but the color is fading. And so this is an evidence of reaction here that's occurring over time. This is precipitation here, where there was no solid in here, but now you see this? Eventually this will settle down to the bottom of the test tube and form a compact solid. But this is just a cloudy, what we call cloudy suspension These are tiny crystals that have formed there, and these white crystals will eventually settle. This is gas formation or effervescence. So precipitation, effervescence. Here, this is like an Alka-Seltzer that has some acid to it, so it's a bubble. Here's some light formation and heat in the flame, heat and light. And so this has observations that you'll see. Here's emission of light with these glow sticks. Sometimes it could be physical, like these. A lot of these instant cold packs are physical change happens. Well, when you dissolve the solid, it gets cold. But they're hot packs, those hot packs that they sell, that's chemical. Okay, are any of the following a chemical change? A firecracker explodes, chemical or physical? A firecracker explodes. Is that a chemical change or a physical change? A physical means that everything's still there as before. So if you have the firecracker, it's filled with powder. Is the powder still there? No. It's replaced. I mean, a lot of heat, light, and gases are formed. Firecracker exploding is an example of a chemical change. How about a puddle of water evaporates? Is that a physical or chemical change?
Physical.
This is a physical because it evaporates into humid air, and you could get that water back. How about a candle burns? Physical or chemical? This is chemical because the candle's no longer there. Eventually it's going to completely burn, and you'll have no more candle left. How about light? Light is refracted into a rainbow. Is that physical or chemical?
Physical.
This is physical because white light consists of all these colors, so you can combine these colors back to make white light. How about this? Sodium metal, sodium metals drop into water. This is, because we don't have a chunk of sodium there anymore. In fact, there's no solid left, just liquid. Also, the color change you can see, but the color change is not due to that. And so when we do chemical reactions like this, we show them reactants here, products here. So sodium is dropped into water, but solid sodium metal is dropped into liquid water, and it forms hydrogen gas and sodium, what's this called? Sodium hydroxide. Yeah. And that's AQ. AQ means it's dissolved in water and some heat. Oftentimes we don't put the energy, so we just balance the mass, but not necessarily the energy here. Because one of the reasons is we don't have the number here for that. The numbers vary. So S is for solid, L is for liquid, G is for gas, AQ is aqueous, dissolved in water. And then we balance it. We balance out the atoms. So this is not balanced here. One sodium, one sodium. Two hydrogens, we have 2 plus 1 is 3 hydrogens on the product side, 2 on the reactant side. 1 oxygen, we have 1 oxygen. So we balance it. We balance it by changing the coefficients here. And so that's one of the things that we try to do. So let's try to balance equation here. Normally we balance it to leave the single elements last. So over here, I usually leave oxygen last here. And so I have 1 aluminum here, but 2 aluminums there. So I need to change the coefficient in front of aluminum to 2. So that'll give me 2 aluminums, 2 aluminums. But we have 2 oxygens here, 3 oxygens here. Do you know what I changed the coefficient on this one to?
32.
I change it to 3 halves. And so I have an extra step in there that they don't show. That's because sometimes it's not so easy to see. And so if I have Al plus O2 yields AlO3, the first thing I'll do is do the aluminum, and so change that. Al2O3, sorry. oxide. Okay, and that gets the aluminum's balanced, but the oxygens aren't. I have 3 oxygens, and then over here I do X times 2 oxygens. So what does X must be 3/2. So that will balance out like that, 3/2. So 2's will cancel, that gives me 3 oxygens, 3 oxygens, and then I'll double everything. So we get 4 aluminum plus 3 oxygens yields 2 Al2O3. This is solid, this is gas, this is solid. And so usually I'd like to leave oxygen or last or any other one that has a single element. Yeah. So let's look at A here. Is that balanced? Now, the first thing is, can you name this? C2H4O. This is a molecular compound because it consists of all nonmetals. Carbon's a nonmetal, hydrogen's a nonmetal, oxygen's a nonmetal. But this is not binary. What's the difference between this and a binary molecular compound?
It has 3 different.
Yeah, this has 3 different elements. So if it has 3, we don't name it. We don't bother to name this. You know, this would be a mistake when people do this. They call this bicarbon tetrahydrogen oxide, monoxide. But that's the wrong name. That rule only works for binary. Like this is a binary molecular compound. This is carbon dioxide. And so that works. This is a binary molecular compound. So this would be called dihydrogen monoxide. That's fine too. This is an element, we can call that oxygen. Is this balanced? Well, to check if it's balanced, we look at the carbons. 2 carbons, over here, 2 CO2s gives us 2 carbons. 4 hydrogens, 2 times 2 is 4 hydrogens over here. 1 plus, how many is this, 6? 1 plus 6 is 7 oxygens. And so this is 2 times 2 is 4. 2 times 1 is 2. And so 4 and 2 is 6. Are the oxygens balanced? Oxygens are not balanced. The reactants have 7, the products have 6. So can you balance this one? So the strategy I use is we save the elements for last. And so in this case, the element would be oxygen, would be last. And so I would have C2H4O plus O2 yields CO2 plus H2O. So I'm going to start completely over. So you should start completely over and then try it. Here. Save the oxygen for last. Balance out the carbon and the hydrogen first. in the carbons first. The 2 there, and then change the 2. And then keep going from there. The oxygen, yeah. So write out the whole thing like this, blank. Yeah. Or looks right. When I start something like this, I'm going to leave oxygen for last. And so I'll just start off with carbon. How many carbons here on the reactant side? 2. Can I change the subscript without changing? Is this still carbon dioxide? No. And so I need to change the, what we call the coefficient. Okay. Now how many carbons do I have? If I have 2 CO2s, I'm going to have 2 carbons. How many hydrogens do I have here on the left? How many do I have on the right? So how can I balance them? 2 in front of the H2O. Okay, then I say this. I do not want to change. I don't want to change this. I don't want to change this, and I don't want to change that because it's going to screw everything up. The only thing I'm going to change is this. Okay, to show that, I do this. I look how many oxygens. I don't want to change this. And so this is going to be fixed at 2 times 2 is, plus 2 is. So I have 6 oxygens on the right, and that cannot change. I don't want to change this because if I change this, it's going to screw up my carbon and my hydrogen. And so this is going to be fixed at 1 oxygen here. And I don't want to touch it. But I'm going to touch this, the coefficient in here. So 1 oxygen plus X times 2 oxygens. So 1 oxygen plus X times 2 or 2X. And so I need to solve for X. And so I'm going to get 1 plus 2X is equal to 6. And so that means 2X is equal to 5. That means X is equal to 5 halves. Is that right? And so if I plug in here 5 halves for X, that's going to be 5 halves times 2 is going to be 5. So 5 plus 1 gives me 6. And so I have 6 oxygens, which is equal to 6 oxygen. But usually we don't want fractions there. So if we don't want fractions there, we'll double everything to get rid of the fraction. If I double everything to get rid of the fraction, then I'm going to get 2C2H4O plus 5 O2s is going to produce 4 CO2s plus 4 H2O. Is that what you guys got? Yeah, I know a lot of you got that, so that's good. But this is the method that we use to solve that.
So how did it become 4s on the other side?
Because you multiply everything by 2. You can't have 5 halves. So you multiply that by 2. And so therefore everything is multiplied by 2.
Okay, so let's try to balance this one. So over here, I have how many carbons? One. Over here, I have 1. So I'm going to fix this. 1 and 1, let's say. At least for the carbons. I might change it. How many hydrogens? 4. And 2. So I'm going to double this one. 2. So I have 1 and 2. So I have 1, 1, and 2. That means oxygen. And so this oxygen is fixed at 2. And this is going to be fixed because I have 2 waters. 2 waters is going to give me 2 oxygens. So 2 oxygens plus 2 oxygens gives me 4 oxygens. It's fixed. And so that means 2x is equal to 4. Therefore, x must be x times 2 is equal to 4. So it's got to be 2. So answer. So this would be balanced at 1, 2, 2, 2. Balance. That's how we balance this one. Oh, sorry. 1, 2, 1, 2. That's how it's balanced. Okay. Draw the number of molecules of each species indicated by the coefficient. So we got to try to draw the molecules here. So this is a CH4 molecule. This is 2 O2s. This is 1 CO2, and then 2 waters. So you just draw them there. You'd have to know what they look like. So. Do the atoms balance? Yes, the atoms are balanced. 4 reds, we still have 4 reds. 1 black, 1 black. 4 whites, we have 4 whites. So the atoms got rearranged. This is an example of a chemical change where things are going to get rearranged. Well, let's try to balance this one. This one's going to be a bit trickier to balance here. But let's try it nonetheless. How many phosphorus? And so it's balanced. Then how many CLs? And so we're going to change this to 5 CLs here. So that's going to change this. So let's go ahead and write that. You could do this in different ways. So the preference is not to touch PCl5, H3PO4, and HCl. And so we're going to add up the hydrogens here. How many hydrogens do we have here? 3 plus 5 is 8 hydrogens. Over here, I'm going to change H2O to 4. And let's hope everything balances. So if I change that to 4, I get 8 hydrogens, and then that gives me 4 oxygens, and I have 4 oxygens, and now it's balanced. So just got lucky. So 1, 4, 1, 5. 1, 4, 1, 5. All right, sulfur dioxide, oxygen, and calcium oxide react to form calcium sulfate. So let's try that. Sulfur dioxide, what's the formula for sulfur dioxide? SO2 plus O2 plus calcium oxide. What's the formula for calcium oxide? Calcium, what's the charge on calcium? Off the periodic table?
+2.
Plus two.
Yeah. Okay. And oxide? -2. So this is 1 to 1. So it's calcium oxide is just CaO. Now, if you're to guess the states, sulfur dioxide, you know what the state is? Solid, liquid, or gas? It turns out it's a gas. Oxygen? What do you think about calcium oxide? Solid, liquid, or gas? Solid. And then this is going to form calcium sulfate. So what is calcium sulfate? Well, I know what calcium is. Calcium is Ca2+. What is sulfate? SO4 2 minus. So it's the same. It's going to be 1 to 1 ratio. So it's going to be CaSO4. What do you think about calcium sulfate? Solid, liquid, or gas?
Solid.
Solid. Most ionic compounds are solids, like sodium chloride, etc. And so okay, calcium oxide is an ionic compound too. Ionic compounds are going to be metal plus non-metals, or made up of ions. Okay, we have oxygen here. Save oxygen for last. And so are the sulfurs balanced? Yeah, okay. We're saving oxygen for last, so we're not going to worry about it yet. The calcium is balanced. Yeah, so what we're going to do is we're just going to change this. And so over here, we're fixed at 4 oxygens is equal to 1 oxygen plus, this is 2x plus 2 oxygens. So basically, it's going to boil down to this. It's going to be 2 plus 1 is 3. And then what we're going to do is this is going to be 2x plus 3 is equal to 4. That means 2x is equal to 4 minus 3 is 1. So x is equal to 1/2. So if we put in 1/2 oxygen here, it should work. So let's check if it works. 2 plus 1/2 times 2 is 1 is 3. Plus 1 is 4. So we have 4 oxygens is equal to 4 oxygens. Do you see that? Well, normally we don't like fractions here, so we're going to multiply this by 2. And so if we double everything, we're going to get 2 SO2s plus an O2 plus 2 CaO is going to give us 2 CaSO4. SO2 is a gas, O2 is a gas, CaO is solid, CaSO4 is a solid. We got that. Okay, let's try to balance out this one here. So how many carbons here? This is tricky. You see, it's tricky because there are 2 carbons here, but there's a 3rd carbon over here. So altogether in this, there are 1, 2, 3 carbons. And so how many CO2s do I need? If I have 3 carbons here, I'm going to need 3 CO2s. You have 3 carbons. And so this will be 3 CO2s. And then I got to count the hydrogens. Again, the hydrogen is split. So I have 5 plus 1. 5 plus 1 gives me 6 hydrogens here. And so how many waters do I need? 3. And so I'm going to have 3 CO2s plus 3 water. 3 CO2s plus 3 water is going to fix the amount of oxygens that I have. So it's going to be 3 times 2 is 6 oxygens. Plus, what is it? 3 times 1. So this is going to give me a total of 9 oxygens over here. And so let me write this up here. C2H5COOH plus blank O2 is going to produce 3 CO2s plus 3 waters. And so what I'll do here is this is fixed, 6 oxygens plus 3 oxygens is going to equal, over here this is fixed too, I don't want to change this. So this is going to be 2 oxygens plus 2x. And so I'm going to get 2 plus 2x oxygens is going to equal 6 plus 3 is 9. So subtract 2 from both sides. I'm going to have 2x is equal to 7, and then x is equal to 7 halves. And so this should be 7 halves oxygen here. And so that's going to be 2 plus 7 halves times 2 is 7. So 2 plus 7 is 9. This is going to be 3 times 2 is 6 plus 3 is 9. So that gives me the right number of oxygens. And then what I'm going to do is just double everything. So I'm going to 2C2H5COOH plus 7O2 is going to produce 6 CO2 plus 6 H2O. So we're going to go on to writing chemical equations. Okay. But I'm going to organize it a little bit differently than the way the book does it. And so I'm going to deviate here. But before I deviate, maybe we should just get some more practice writing chemical equations.
We're going to talk about synthesis and
Yeah. We'll talk about synthesis. But let's look at some examples of chemical reactions first, and then we'll look at predicting chemical reactions. So what would you call this? Magnesium or magnesium ion?
magnesium.
And what do you call the other stuff? Nitrogen or nitrite would be with a T, nitrate.
Yeah,
You would have to have an oxygen in there.
that's right.
Yeah. Oh, so there's no oxygen, so it would be a D. Nitride or nitrogen? Nitride would have what charge? Like oxide has -2, nitride would have -3, based on its position in the periodic table. But this is not nitride. That's nitrogen, elemental nitrogen. And so this is what we call a redox reaction. So we take magnesium, solid metal, plus nitrogen. Magnesium tends to lose electrons or tends to gain electrons? Lose. And so if magnesium loses, how many electrons does magnesium lose? 2. So what we're going to form is Mg2 plus, magnesium ion. And then nitrogen wants to gain how many? 3. And so nitrogen with 3 electrons is N3 minus. And what we need to do is we need to get the right ratio. How many magnesiums, how many nitrides do we need to add up to 0? That is the charge. Yeah, and so one of the tricks that people do is they do this. To figure out the formula quickly, we'll use this as a subscript. This is like cross multiplying. We'll use that as a subscript there. And then essentially it's the same thing as cross multiplying. So we'll get Mg3N2. And we call this magnesium. It's an ionic compound, so magnesium nitride. Since it's an ionic compound, we don't use the prefixes, so we'd never call this trimagnesium dinitride because it's metal and non-metal. If this was all non-metals, we would call it tri and di. That's not the case. So we take magnesium metal plus nitrogen, gives us magnesium nitride. And so now we need to balance this. I don't want to mess with this ratio here. So what I'll do is I'm going to change the magnesium. Magnesium is going to be what? 3. And then nitrogen will be just 2. And so now it's balanced. And so we'll need 3 magnesiums, 1 nitrogen to form 1 magnesium nitride. This is called a redox reaction. The oxidizer takes the electrons, so nitrogen ends up taking electrons. This is what we call the oxidizer. Oxidizer is on the right side of the periodic table. And on the left side, we have something called the reducer. And reducers are on the left side of the periodic table. Those are the species that lose electrons. And so nitrogen is not a very good oxidizer. Oxygen is a much better oxidizer. And so oxygen is great at oxidizing metals, but nitrogen can do it too sometimes. Or something like this, but it's not nearly as effective. Your book calls this a combination. I call this an element plus element redox or combination reaction. So it's redox. Element plus element combination. They're going to combine. One element loses, the other element gains. Let's name this one here. What's this called? ZnOH2. Zinc hydroxide. What's the charge on zinc? +2. Shouldn't we call it zinc Roman numeral 2 hydroxide? It's fixed charge, right? Zinc, cadmium, and silver. So this is zinc hydroxide, which is ZnOH2. What's this one called? Well, we recognize this is an acid. It's an acid because it's neutral and it begins with H. And so acid names are going to be based on the anion. So what is the anion here? The anion is SO4. And what's the charge on that anion? So SO4, 2 negative. And what do we name this? Sulfate. So if this is sulfate, then we change the ending to ic, acid.
Hydrosulfuric acid.
We don't do hydro because hydro is if this were I. And so it's tricky. And so this would be hydroic acid. But I would be like this, S2 minus. And so hydrosulfuric acid is actually H2S. This one which should be called sulfic acid, but sulfic acid doesn't sound right. You know what they call this? Not sulfic acid. They call it sulfuric acid, so they add a little bit here. Sulfuric acid. But technically it should be sulfic acid. We call it sulfuric acid. So zinc hydroxide plus sulfuric acid. Now, they have a DR here. And DR stands for double replacement. Double replacement reactions, we just switch the anions. So what we're going to do is this. We're going to try swapping anions like that. in a double replacement reaction. And so what is this going to produce? We'll just go down here. And so that's going to produce zinc with sulfate. So we should form zinc sulfate. And then we're going to form hydrogen with hydroxide because the cation is hydrogen ion. And so what is hydrogen hydroxide? Do you know what hydrogen hydroxide is? It's another name for, there's so many names for water. You know, water we could call dihydrogen monoxide. We can call it, you know, what did we call it earlier? Oxic acid, hydroxylic acid. We can call it hydrogen hydroxide. Zinc sulfate is a zinc ion with the sulfate ion. And so what's the proper ratio of zinc to sulfate? 1 to 1. So the formula for zinc sulfate is ZnSO4. And then hydrogen ion is H+, hydroxide ion is OH-. That's the hydroxide ion. So we take the hydrogen ion, combine it with the hydroxide. We ignore how many we have. We just want to get the right formula. And so how many hydrogens and how many hydroxides do I need? 1 to 1. And so that's going to give me HOH, or HOH is also called H2O. Now, when I balance this out, I balance it by ions. When we have double replacement, it's easiest to balance by ions rather than balance it by atoms. So let me show you what I do here. I have one zinc ion here in the reactants, and I have one zinc ion in the product, so the zinc's already balanced. I have how many hydroxides here? I have 2 hydroxides here, and that means I need 2 hydrogen hydroxides. 2 hydrogen hydroxides are going to make 2 waters. Like that. And then I have 2 hydrogen ions. Well, the 2 hydrogen ions are already balanced out because I'm going to have 2 hydrogen hydroxides. And then I have 1 sulfate, and the sulfates are balanced out. You see? So now it's balanced. And so this is a different type of reaction. This is called a metathesis reaction, or a double replacement reaction. Okay, let's look at the next one. It's going to be, what's that? Zinc or zinc ion? That's zinc. And what's the other reactant? Iodine. Okay. And so this is the reaction between zinc and iodine. So we'll go. What time are we out here? 4:55. Okay. We'll have to continue this next time.